We now return to the question of how to compute the derivatives of a function based on a formula, not from a graph, but from a formula. And just as a reminder, all of the work we're going to do comes back in principle to this definition: delta y over delta x, delta f over delta x, what's the change in f divided by the change in some interval, and then letting that interval shrink towards 0. The more common symbols used when we're dealing with formulas are f prime, ddx of f, or insert y here, or other variables, but the dependent variable and the independent variable in this d form. It's called Leibniz notation. Now, we indicated earlier that working with this definition can be pretty cumbersome, and anyone who's had a calculus class before this will be a review. There are ways to get these derivatives much more quickly than trying to apply this definition. So essentially, other people have figured out that if we apply these definitions, this definition here, to common functions like exponentials and polynomials, we can get the derivative just by some patterns. And here are a large number of them. If we ask, what's the derivative of a constant function? So in all of this, in all of these examples here, k is a constant. What is the derivative of a constant? Well, we're going to say the derivative of a constant is 0. There's an important realization behind that, which is that if we have a constant function, say we had a function that was y equals 2, we can associate this back to the idea of slopes. If we have a constant function y equals 2, the slope is what on that graph? Well, the slope is always 0, regardless of where we check. And so the derivative, which is the way to calculate the slope on a graph, will always equal 0 in this case. So do remember that all of these derivative rules harken back to and have parallels in the graphical world. Sometimes they're obvious, like this one. Sometimes they're a little less so when we get to the more complex rules. All right. Polynomials. Polynomials are built up of powers of x, and fortunately the rules for the derivatives, or finding the slopes of powers of x, is straightforward. What happens when you have x to the p? The derivative of that will be p x to the p minus 1. And for an example, if we had x cubed, and we took the derivative of that, we would get 3x squared. Now, things we can say about that as an expression are bring the power down front, and then subtract 1 from the power. That's the most typical way students learn to memorize this particular rule. So if we have a power of x, you bring the power down front, subtract 1 from the power. There are also some nice simple rules when it comes to the addition and subtraction of functions. If we're asked to take the derivative of the sum of two functions, we can just take the derivative of each one separately. So that's going to come in very handy. Same thing for subtraction. The other rule that comes in very, very handy as well is that if we have a constant times a function, notice up here, constant by itself, here we have a constant times a function. When we take the derivative of that, we can bring the constant out front. And then take the derivative of the inside. Now, how do these two rules here work together? Well, here there is no function, or if you like, the function is just 1. So even if we brought the function or the constant out front, we would have k times the derivative of 1. And we already said the derivative of any constant is 0. So the derivative would still be 0. Even if we tried to use this rule, we would end up with the same value. Keep that in mind as you go through the derivatives. Sometimes there's choices about which rules you can use. They will all lead to the same function in the end. They have to. So never feel like you have to pick the right rule. If a rule applies, it is by definition the right rule. Okay, let's get some practice here. And if you've seen derivatives before, it's probably a good idea just to try these on your own first. Pause the video and then see how you do. All right. So using our power rule here, the derivative of x to the 4 plus 3x squared, bring the 4 down front, keep the x, and have 1 less power, that's cubed. The next one I'll do in a bit more detail than you'd usually do in practice, but we're also going to follow up by taking the derivative of 3x squared. We'll keep the 4x cubed. What we're going to use is that rule where we can bring any constants out front. So we have 3 times the derivative of x squared instead of the derivative of 3x squared. And the derivative of x squared is 2x to the power 1. And of course, we don't usually put the power 1 in there. So we simplify down to 4x cubed plus 6x. So if we wanted to know the slope at any point on this function, on this graph, this formula would give us the value of the slope. All right, let's do a slightly more complex example here. The only issue here is pi, just remember, is a constant. The other tricky part here is the x to the, oops, I was about to say it already. The only tricky part here is the square root of x, which can be written in power form. So this is a good idea before you start taking derivatives, is to convert all roots to powers. Because we have a rule for powers and their derivatives, we don't really have a rule for the square root and its derivative. All right, so taking this pattern we just saw before, where this 3 ended up being multiplied by the derivative of what came afterwards, we can jump straight to the derivative here. Let's do a little side chain. So the derivative of 2.6 something is 2.6 times what we get when we differentiate x to the 1/2. Well, we bring the power down front, and then we get x to the 1/2 minus 1, which will be negative 1/2. And that completes the derivative of the first term. The next term, minus a constant, pi stays there. The derivative of x cubed would be 3x squared. And last but not least, the derivative of 4, which is a constant by itself, not multiplying anything, would have a derivative of 0. And this is correct, but it's usually a good practice to tidy things up. And for our own notational practice, it's good to recognize that x to the negative 1/2, there's a few ways we could write that. We could write that as 1 over x to the 1/2, remembering that negative powers are reciprocals, 1 overs. And we'd usually put the 3 before the pi. And last but not least, we could write this x to the 1/2 as a root of x. So any of these versions are correct. All of these versions are correct. This one, sort of an intermediate phase. This is more easily read, I think, for most people, but they all are and represent the derivative of the original function. All right, if you'd like to do one yourself for practice, just to get back into the swing of things, try finding the derivative of negative 3x squared minus 1 over x squared. If you want to pause the video, I'll give about 3 seconds of silence here. All right, computing this derivative, we could try to match it, but quite frankly, it's just as easy to go through the calculation. The only thing I would recommend, again, is if you have a power like this, is to convert negative or convert rational functions or ratios into regular powers, or convert x in denominators to simpler negative powers. So this 1 over x squared could be written as minus x to the minus 2. We're going to subtract x to the negative 2. And again, the reason for doing that, it makes your life easier when you talk about the derivative, because we know the rule for that. So derivative of negative 3 anything is negative 3 times the derivative of the x squared. Then we have the derivative of x to the minus 2, bring the power down in front, and subtract yet another unit, or another 1 from the exponent, and we get x to the negative 3. And that would look like minus 6x plus double negative plus 2 over x cubed. And if we scan down the list here, number 2 here would be the correct answer. All right. Here are a few more commonly used functions, our exponentials and exponentials with a different base. For example, 2 to the x. What is its derivative? Just like e to the x, which has the simplest derivative rule, the derivative of e to the x is e to the x. That's perhaps surprising, and it relies very closely on this base being the special base of the natural exponential e. You'll notice here, when we have a different base, the derivative is almost the same. The derivative of 2 to the x is 2 to the x, but with a little scaling factor of ln of 2. If we apply that same rule here, the derivative of e to the x would be e to the x times ln of e. Oh, but ln of e is just 1. So this rule always works. This rule is something that we're going to rely on most closely because e to the x is going to be our function of choice, precisely because it avoids this nasty extra factor. The other derivative rule that's going to come in handy is for logs. In the natural logarithm, again, like the e to the x, it has a nice simple form. The derivative is simply 1 over x. And when we have a log with a different base, we get the same pattern. It's still 1 over x, just like ln, but with an extra scaling factor of 1 over ln of the base. And again, if we use this rule all the time, it would work. Even for log base e, we'd get 1 over x with ln of e. But it's easier to remember this short and fast rule. If you use the natural base e ln, then the derivative is simply 1 over x. All right. Again, a little bit of practice. Let's find the derivative of this combination here. So the derivative of 4 times anything will be 4. And here you have to notice where the x is. X in the exponent and a constant base. This is an exponential function, like e to the x. Distinguish it from this one here, x to the 4, where this is a polynomial. I guess technically a monomial, but a power of x. Constant exponent, and x is the base. So the rules of for these two different functions are different because they're different functions. This is an exponentially growing function. X to the 4 is a polynomial. It grows, but not as quickly as 10 to the x. So the first challenge is to recognize that. Once you do that, then we can take the derivative of the 4 times something. Well, it's 4 times the derivative of 10 to the x. We said the derivative of any exponential is the same exponential again, but with a correction factor of the ln of the base. So again, you can always flip back to the previous page. This is the scenario. We have 10 to the x. We get 10 to the x ln 10 as our derivative. Moving to the next term, we have plus the multiplier, and then the derivative of x to the 4, that's the bring the power down front, subtract 1 from the power rule. So bring the power down front and subtract 1 from the power. And if we wanted, we could clean that up a little bit. 4 times ln of 10 are all the constants, times 10 to the x, plus 40x cubed would be the derivative of that function. Let's do another one here for practice. Here's the easiest one. The derivative of e to the x by itself is just e to the x. The derivative of log 10 of x, okay, the derivative of any log is 1 over x, and then there's a correction factor. It's the opposite, which is reasonable, of what you get with the exponentials, because logs and exponentials are inverses. The scaling factor, when we take the derivative of a log or a ln, is 1 over log of the base. 1 over ln of the base, more particularly, base e ln there. And quite frankly, the most common mistake is to get confused between these two rules, 10 to the x or x to the 10, which is a power, which is an exponential. If you can be careful about that and just think back to e to the x is the simple one, so if the x is in the exponent, It's the fairly simple, the derivative is the same function with a scaling factor. And when x is the base, it's a polynomial. Bring the power down front and subtract 1 from the power. And that introduces all the core functions, except for trig. We'll get to those later on in this unit. But what we're going to need to do next is expand our potential for handling exponentials and logs, because here they're pretty easy, but they don't typically show up like this in formulas. So we're going to see how adding factors in the exponent can be handled with other derivative rules.